Good evening, Professor.
Yeah. I think in this last class we have talked about crack resistance, right?
Yes, sir.
Yeah. Okay.
Good evening, sir.
Yeah. Good evening.
Good evening, sir.
Good evening, everyone. So we'll get started because I think we have enough people. So as we have discussed in the last class, we understand what is the energy release rate G, right? Depending on the value of sigma. Suppose if you are applying sigma 1, for a given sigma 1, the energy release rate is, so for example, if I go to the previous slides, right? Depending on the scenario, it could be in this particular problem for a double cantilever beam, it is a function of square of the crack length. Sometimes it could be linear function. So the point is, if you are calculating the energy release rate for a given sigma, it varies as a function of crack length. And now this red curve, I'm reiterating what we have done in the last class. The red curve is what we call the crack resistance, or in sometimes fracture toughness. For example, let us look at this particular problem. This is a scenario for a brittle material. For a brittle material, the fracture toughness is a constant. So, for example, this is the resistance of the material, right, for a given crack length. So let's say this is the crack resistance. Now, if your energy release rate G is like this, what is the meaning of that? So suppose if your crack length is this, the energy release rate is this, isn't it? That means which the energy release rate is less than the resistance, and hence crack will not grow. And until the crack length is this critical crack length A naught, right, the crack will not grow. But then at this point of time, the crack will suddenly grow because the fracture toughness, the energy release rate is much higher than the resistance to the crack. That means the constant resistance scenario, which is for a brittle material. Is that concept clear to all of you? Now, if you go to the ductile material, what happens in a ductile material is you will have some, for a given system, you will have some fracture toughness or material resistance. But as the crack grows, the crack initially is very sharp, but because it is a ductile material, the stress state ahead of the crack tip is going to be very high, and that is going to cause plastic deformation. And as a result, the crack, which is initially to begin with was a sharp crack, would now become a blunt crack. So what do I mean by that? So at this point of time, the crack was like that at this instance, but then when the crack has grown from here to here, it will not remain a sharp crack anymore. It will become a blunt crack. The moment it becomes a blunt crack, the resistance to fracture will reduce because the area, the radius is increasing, right? So the local stress state ahead of the crack tip is not going to be as high as what it would have been when it is a sharp crack. And as a result, because the crack is becoming blunt, and hence for the same load, the local state of stress is going to be reduced, and hence the material will not fail at the same load. And that is what we see as increase in the resistance. And that is why, as with increase in crack length, the crack resistance increases. But now the question is, the rate at which, the rate in the sense with respect to the crack length, at which the resistance increases, if that is higher than the increase in energy release rate, then the crack will not propagate. But if the rate at which the crack energy release rate increases with respect to crack length increase is more than the rate at which the resistance increases, then the crack will propagate. That means the slope of this line, as long as the slope of this line on this curve, the red line is greater than the slope of these lines for different slopes, for different sigmas, if this slope is greater than this slope, then the crack will not propagate. Otherwise, the crack will propagate, right? In an unstable manner. So now let us look at what are the conditions. How do we write these conditions? So condition for unstable crack growth is that first of all, G should be greater than or equal to R, but that is not enough, because even though G is greater than R here, if you look at this particular scenario, G is greater than R, but if the crack length is only A1, then the crack will not grow unstably because this slope is larger than this. So from this length to this length, it will grow slowly. And after the crack becomes a length of A2, in the case, if the load is sigma 3, you will see that the rate at which the slope of this line is larger than the slope of this line, and that is when crack grows unstably. But if your load is only sigma 2, you can see that G is, so for example, if your crack length is A0, and you would see that the G is always greater than this fellow, and hence it will not grow. But the moment the crack resistance increases, then crack will go from A0 to A1. Crack will not go beyond, for sigma 2, where the loading is sigma 2, crack will not go beyond A1 because the resistance is larger than G. Although you are increasing G, always your resistance has been greater, and hence it will not increase. So there are two conditions that needs to be met. If G is greater than R and dG by dA is less than dR by dA, crack may grow in a stable manner. But when these both conditions are met, crack will grow in an unstable manner. Okay. So now we have looked at the state of stress ahead of the crack tip when you have a elliptic hole in the material, because that depends on the crack radius, crack tip radius. But now if you have a mathematically sharp crack, mathematically sharp crack, then the state of stress ahead of the crack tip, which is mentioned in the polar coordinates r and theta, let us say you take a point here and the positions are r and theta with coordinate axis here x, r and theta at the crack tip, then, and the body is actually subjected to sigma 2 in this case. Although the body is subjected to sigma 2 at an angle theta, you will develop the stresses sigma 11, sigma 2, sigma 12 as a function of r and theta, right? Where r goes into the denominator, and you would see that when r is equal to 0, then all these guys will blow up. They become infinity. That is for mathematically sharp crack. But in reality, what happens is you will not have mathematically sharp crack, and there will be some finite value for this r, and hence your stresses will always be bounded. Okay? Is that clear? And if you carefully look at this fellow, this sigma 11 or sigma 22, for example, if you take sigma 22, that is sigma root pi a. That means this numerator is depending on far field stress sigma and a in the denominator. And this, you see that this is a plate, infinite plate with a central crack whose length is 2a. And here you have a semi-infinite, semi-crack length. So this sigma root pi a will sort of tells you by how much amount this stress is getting intensified, right? Because this sigma is applied stress, depending on the crack length, the stress intensity going to be there, and this is why it is called stress intensity factor. So K1 is a sigma root pi a, for a being much smaller than plate size, and this sigma root pi a can also be written as root 2 pi r sigma 2 at any r where theta is equal to 0 as r tends to 0. So what do I mean by that? If you plug in this equation theta equal to 0, then cos 0 is 1, this is 1, so sigma 2 cos 0 is 1, and sin 0 is 0, so this will become 1. So sigma 2 at theta equal to 0 will be sigma root pi a by root 2 pi r, and you can see sigma root pi a is K1 is equal to sigma 2 times root 2 pi r. That is what we can write. K1 is equal to sigma root 2 times root 2 pi r is your what we call stress intensity factor. And it's a very important quantity in fracture mechanics. And the unit of K1 is very interesting. This is MPa and there is R in the under the root. So the unit is MPa root meter for stress intensity factor. This is very different from stress concentration factor, which we have learned in the static, in the case of notches, where stress concentration factor is dimensionless, whereas stress intensity factor is dimensional. Keep that in mind. So now I can replace sigma root pi a in the previous equation with K1. So sigma 1, sigma 2 to sigma 1, 2. So that means this is the stress field ahead of the crack tip. And using that, you can actually compute the displacements. The displacement. So you please pay attention carefully. As R tends to 0, the displacements become 0. Isn't it? But the stress goes to singular, infinity. This is a pure elasticity solution, which is only of mathematical interest, because in reality, you will not have a pure elasticity ahead of the crack tip. As soon as you apply some force, immediately plasticity develops. So the stress state ahead of the crack tip, which can actually be seen through these photo elasticity fringes, this is for a plane stress case, which actually describes the plot. If you would plot these things as r theta coordinates, this is how this looks like. Okay, this is a shear stress plot. So if you would plot sigma 1, 2, that is how it looks like. Similarly, you can plot sigma 1, 1 and sigma 2. Okay. So now the effect of a crack on strength. So upon application of a load to a structure with a crack, the crack may suddenly grow and cause failure by brittle fracture. That is what we have discussed. From fracture mechanics, we know that there is a useful quantity called stress intensity factor K1. Here it is written K1 because the loading is mode 1 loading. That is why it is called K1. Otherwise, K is your stress intensity factor, which describes the severity of the crack situation. If your A is large, then it is much more severe. The crack intensity is much more severe. Okay, is that clear? Whatever I said just now?
Professor, in previous slide, there was some equation in purple color, sigma 3,3. Can you explain that?
Here we are actually considering.
In previous.
Yeah. We are considering plane stress case. Because it is plane stress case, sigma 33 will be 0, and hence, and we know that sigma 33 will be dependent on, in the plane stress case. In the plane strain case, epsilon 33 is equal to 0, and hence sigma 33 will depend on sigma 1 and sigma 2. If you are talking about a plane problem. Okay.
Thanks, Professor. Yeah.
So now we have seen K, equation of K is sigma root pi a. So it depends on stress, applied stress, and the crack length. So K is affected by crack size and stress. Not only that, this equation that we have given is only true for a plate of infinite size. But if you bring in a finite size, the size effect, the plate size and plate geometry effect should come in, and hence there will be a factor before that. Then instead of K1 being sigma root pi a, it will be some factor beta times sigma root pi a. Beta is what we call geometric factor. So the K is affected by crack size, stress, and geometry when the material is assumed to be linear elastic. So now we can, earlier what we said was the crack will grow when the energy release rate G is greater than critical energy release rate GC. That is when crack will grow. Now we can say that a crack will grow when the stress intensity factor K is greater than fracture toughness, Kc. Kc is your fracture toughness, that is the material property. Whereas Gc is critical energy release rate, Kc is what we call fracture toughness. So as long as your stress intensity factor, that is sigma root pi a, is less than Kc, no problem, the crack will not grow. But if this is becoming equal to Kc, then the crack will grow. In this class, we are only focusing on purely linear elastic fracture mechanics, which is nothing but brittle fracture. So we are not talking about fracture toughness depending on the size of the crack, which was the case here. Here the fracture toughness dependent on the size of the crack, that is for the ductile material. Whereas for a brittle material, fracture toughness is independent of the crack size. So in that case, as soon as K, as long as K is less than fracture toughness, Kc, then this is also called critical stress intensity factor. K is your stress intensity factor, Kc is fracture toughness or critical stress intensity factor. As long as K is less than Kc, the material will not fail, otherwise it will fail. Okay? Any questions?
Sir, we are only dealing with mode 1, right? Not
Mhm,
mode
mhm.
3, nothing.
Mhm.
In general, this will be not the case, right? Like
No.
you will
In
have a
general,
mixed mode or something.
you will have a mixed mode fracture, but you can also find mixed mode fracture toughness. Okay. Similar to what we have for three-dimensional state, we can also generate something called a similar scenario for fracture problems also.
Okay.
Is that clear? Hello?
Yes.
Now, let us look at the stress intensity factor in a little bit more detail. Let us say you have a plate whose width is 2b and semi-crack length with an elliptic crack whose semi-crack length is a, or the total crack length is 2a. Okay? So you have a plate with a central crack and remote stress applied is S. The stress intensity factor K is, this 0 should not be there. I'm sorry about it. K is given by sigma root pi a, that is S root pi a, is valid only when A is much, much smaller than B. That means crack size is much smaller than B. Right? That is above relation is true only when this is there. And now if you look at this fellow, you hear we are actually computing on this guy. We are applying for different crack length. Suppose let us say crack length is 60. At that crack length 60, with B is equal to 152, T is equal to 1.5 mm. Out of plane thickness is 1.5 mm. B is 150 mm. When you do this uniaxial tension sort of a thing, a mode 1 loading, then we measure when does the crack suddenly grow, when does the fracture happen. And it is found that it happens at about 20 ksi or close to 150 or 120 megapascal. And if I reduce the crack length, my load at which the failure happens reduces, and that is how the data has been given. Okay, and you can see the fracture toughness with this data. You can fit a line for this equation. The Kc, S and A, if you fit an equation, fit a line, from there you can calculate Kc is equal to S times root pi A, because this is corresponding to failure. And that is your S, you know, right? From there you can calculate S is whatever you are applying, and S is equal to, you will get 66 ampere root meter. And S is P by 2 beta, that is equal to sigma naught into 1 minus 1 by B, where sigma naught is, when there is no crack, what will be the theoretical what you call threshold crack length. Okay. So here you see that this is a solid line and this is dashed line. And when you are plugging in this S sigma root pi A, this will be the line, but it will deviate from the LEFM because when the load is very close to the yield strength of the material, it will deviate because then the fracture toughness, when the stress applied goes close to the yield strength of the material, then there will be plashing deformation. Then this equation itself is not valid. Okay. So from there you can estimate what is the stress intensity factor. And so now what you are saying is when the dimension is far away, this matches, but the dimension of A becomes much larger than B, then we have to account for some variation in the geometry. So there are,
Sir,
yeah.
So there we said about two equations, right? So one is the stress intensity factor and another one is the critical stress intensity factor, right? So
Correct.
both has the same equation, Professor. So
No,
how,
that is that the reason for that is if you take sigma is equal to load by area, correct?
Yeah.
When the material is yielding, right? What will that sigma be? That will be yield strength, sigma y.
Yeah.
Sigma y is equal to Py by A, where P is the area will remain constant, P is the load corresponding to the yield strength, isn't it?
Yes.
Similarly, if K is equal to S root pi A, right? If you fix a value of A, then if the fracture is happening, corresponding to that fracture, what is the S, right? Suppose, what is S means what? The failure strength. That means wherever the, for example, in this particular figure, let us say my crack length is 35 mm. Okay? For a 35 mm crack length, I have done the experiment and I found that at approximately 200 MPa, the material has broken. Then the stress intensity factor corresponding to that scenario is what we call fracture toughness, isn't it?
Yes, sir.
That is why I have taken crack length A and I have verified, I have applied the load and at which load is failed. That is what I am calling it as SC. And SC times root pi A becomes my KC, isn't it?
Yes, sir.
Yeah, that is what it is.
Sir,
Thank you,
one
sir.
small question, sir.
Mm.
I mean, I get the point on the stress intensity factor, but I'm not able to understand the difference between the energy release rate and the stress intensity. Are they like
They are connected items. So the unit of energy release rate what?
joules
Joule
per?
per meter.
Ah,
Joule per meter. This is MPa root meter. They are two different quantities, but they are connected. I will show you the relationship between K and G in a moment. Okay.
okay.
Yeah. Either you can use, see what energy release rate, I'll tell you why these two quantities, you can either use G or K in order to qualify whether a crack is going to propagate or not. Okay.
Okay.
Yeah. So we will talk about it in a moment. So people have done these tests and then to compute fracture toughness, people have done various experiments and then you can see for different grades of steels, what is the fracture toughness, what is the yield strength, ultimate strength, percentage elongation and so on. This is for steels of different kind and this is aluminum and titanium alloys. This is for polymers. This is for ceramics. The fracture, mode 1 fracture toughness. K1C means mode 1 fracture toughness because that is the most important requirement. It is very similar to yield strength is measured in the uniaxial tension scenario, right? You always measure yield strength for uniaxial loading. Here also, the fracture toughness is usually reported for mode 1 loading. Okay. So this data will be available like the yield strength data is available for most of the materials. So as we have said, if the failure stress, that means the sigma naught, is equal to the yield strength of the material. So the SC is equal to, so the failure stress is SC, right? If that is equal to the yield strength of the material, then we define AT. AT is what? When the failure stress is equal to yield strength of the material, then that is what we call AT. In the previous equation, here we have calculated AT, no? What is the AT value? That is basically, it is not necessarily 0, the threshold crack length when the fracture happens at a stress equal to the yield strength. That sigma naught is your yield strength of the material. Here we are talking about what kind of material. Did they mention the material type? They did not, but 518 MPa is for some material. It may not be here, but it is some steel in this region. So you should always design components based on the fracture mechanics if the cracks longer than AT are found in the structure. Because if the cracks smaller than AT are found, then it is very likely that the material is going to undergo plastic deformation, right? Suppose if you want to study more design components, you should check what is my AT, and your design should be based on fracture mechanics if your crack lengths are longer than 80. And you should do the design based on strength. That means you need not worry about fracture mechanics based design if the cracks are shorter than 80, as the behavior is dominated by yielding. And the central assumption in making these two approaches is that center crack plate with a crack length being much smaller than the plate size. Meaning the crack length is much smaller than the plate size, which is more or less okay in this scenario. But if you have a change in geometric conditions, that will also have an effect on threshold crack length, which is there to decide whether you want to design based on strength or based on the fracture mechanics. So in order to account for that, you add a geometric correction factor. Okay. So now let us look at the brittle versus ductile. So let's consider a case 1. You have a material which has very low yield strength and very high fracture toughness. What happens when you have very low yield strength? Whatever stress that you are applying, the material is going to immediately see plastic deformation, right? So if you have very low yield strength, you will have, if you look at this picture, this is the residual strength and this is crack length. If you are considering only yielding, that is this line, low yield strength, that the material will have this yield strength and then it is reducing, and very high fracture toughness. And here you are talking about very high yield strength. So the stress is not saturating, it is saturating somewhere here, right? And low fracture toughness. So when we say very low yield strength and very high fracture toughness, you have a relatively large value of transition crack length. The transition crack length will be very large because if you look at this equation, AT, sigma naught is very low, Kc is very high, and hence you have very large value of transition crack length. That means the crack length, the transition crack length is somewhere here, which goes from linear elastic fracture mechanics to yielding phenomena. So you have at a very large crack length, you have transition, and hence you really don't need to apply fracture mechanics approach because usually the crack lengths will be shorter than this transition. So I will talk about this Boston molasses tank failure at a later stage when we are talking about fatigue failure. Right now, let us not worry about it. And case 2 is very high yield strength and low fracture toughness. If you have very high yield strength and low fracture toughness, this transition crack length is going to be very low. That means transition crack length is very low. If the transition crack length is very low, then you will, most of the cracks that are there in the material are going to be larger than this transition crack length, and hence you need to adopt fracture mechanics approach for the design. And we know for brittle materials, we have very high yield strength, or actually there is no yield strength, it is actually ultimate tensile strength. and low fracture toughness. And hence, in brittle materials, the transition crack length is very low, and hence even a small crack can be a dangerous crack in brittle materials because the transition crack length is very low. Okay? All right. Now let us look at the stress intensity factor. We said if you have a crack length whose size is much smaller than the component size, then you can use K1 is equal to sigma root pi a. But if the dimensions are comparable, the specimen size and the crack size are comparable, then you need to add a geometric correction factor F here. F is here is the geometric correction factor. So your K1 will not be simply sigma root pi a, F times sigma root pi a. Sigma is the far field applied stress. In this figure, what is sigma? Sigma is my SG. SG is the gross stress that I have, a far field stress that is being experienced. So now there are various scenarios. For example, you say this is my A and that is my B. This is for a central crack. This is for an edge crack, double edge crack. Both edges have cracks, and a single edge crack. Okay. And stress intensity factor is given as F SG root pi a, whereas SG is equal to P by 2 BT or P by BT, depending upon what you are talking about. For example, in this figure, this is B. In these two figures, it is 2B. So the denominator, whether it is 2B or B, basically this is the area of that area you are talking about. Now, typically, the geometric factor is computed using these formula. What is this? F is equal to 1 minus 0.5 alpha, whatever. Alpha is the ratio of A by B in any geometry. This is the equation when H by B is greater than or equal to 1.5. What is this? This is height and this is the width of the specimen. Okay. And if H by B, this should have been less than or equal to 1 maybe. This is not greater than or equal to, this should be less than or equal to 1 because this is greater than or equal to 1.5 and 1.5 it is greater than 2, that is this, and this is less than or equal to 1. This is what you need to use. But these are complex equations, but if you are allowing 10% error on F, then depending upon the A by B ratio, you can say K is equal to S root pi A. If A by B is less than 0.4, you need not have any geometric factor. But if it is larger than that, larger than that value, then you have to add geometric correction factors. Okay. In any way, one can compute these geometric correction factors using the formula that are available. Okay. So now let us look at this problem.
So one quick question. That A by B ratio for the third case, 0.13. That also same expression or?
Yeah, I think I probably have made a mistake. 1.24 maybe. When I am typing, I would have made a mistake.
Okay.
But these numbers I will give you. Yeah.
Thank you,
okay.
sir.
Yeah. I'll give you those numbers. No worries. Now, a center crack plate, that is this is the center crack plate, has dimensions B is equal to 50 mm, T equal to 5 mm, and large H. A force of P is equal to 50 kilonewtons is applied. Large H means you can take H by B to be much larger, something like that, right? Or maybe, yeah. Now, what is the stress intensity factor for a crack length of 10 mm? If your crack length is 10 mm, what is the stress intensity factor? What is K1 for a crack length of 30 mm? What is the critical crack length for fracture if the material is this? Okay, this is the question. So, from the data provided in the slide, this is the material, right? 2014 T651 aluminum. 2014 T651 aluminum is 24 MPa root meter is the fracture toughness, K1C. K1C is 24 MPa root meter. And we calculate SG is equal to P by 2 BT, that is 100 MPa. For A is equal to 10 mm, alpha is equal to A by B, that is 10 by 50, that is equal to 0.2, right? That is less than 0.4. So I need not use any geometric correction factor. So I can calculate what is my A is 0.4. So for K is equal to 10 mm, I can use K1. That is 17.7 ampere root meter. So what is the, for 10 mm crack length, what is the stress intensity factor? I got 17.7 ampere root meter, which is less than 24 ampere root meter. And hence, will the crack propagate or not?
No.
No. Now let us look at 30 mm. 30 mm is A by B is equal to 3 by 5, that is 0.6. So that is greater than 0.4. You could take one of them, or you can actually use the formula. So you are using F is equal to 1 minus 0.5 alpha plus 0.226 alpha square root of 1 minus alpha. That is giving you 1.292. So K1 is 1.292 Sg root pi A, and that is 39.7 ampere root meter. For 30 mm crack, for the same load, the stress intensity factor is going to be 39.7 ampere root meter. So will the crack catastrophically grow or not?
Yeah, unstable.
It will fail. It is very similar. So you need to compute in normal static failure theories. You are computing stress and comparing that with yield strength of the material or ultimate strength of the material. You are computing an equivalent stress and comparing it with the yield strength or ultimate strength of the material. In fracture mechanics problem, you compute the stress intensity factor and check whether the stress intensity factor is less than fracture toughness or critical stress intensity factor or not. Excuse me. Okay. If your computed stress intensity factor is less than the fracture toughness, then the material will not fail. Otherwise, the material will fracture. And hence, you need to change your design accordingly. Okay. Now, this is another problem. Is a wall. You have a wall. Okay. Whose thickness is 12 mm. Okay. This is the wall whose thickness is 12 mm. Has a flaw of 5 mm deep. So crack length is 5 mm. Determine if the wall will support a tensile load of 172 ampere. If the wall is experiencing a 172 ampere load, whether it will fail or not. The fracture toughness of the material is 24 ampere root meter. And you should compute K1 using this formula, where normally it is sigma root pi A, sigma infinity is the far field stress. And this quantity root secant pi A by 2t is your geometric correction factor, because it has certain what do you call, finite size. Okay. So how do you solve this problem? There are two ways. Because K1 is sigma root pi A is for a central crack problem. So all that I can do is I can create the equivalent central, I can create a mirror symmetry, and then this can be seen as a central crack with length 2A, right? And K1 is that, so I can compute K1 and see if a failure occurs if its K1 is greater than or equal to K1C, otherwise it does not. So I compute K1, sigma root pi A is half crack length, root of secant pi into 5 by 2 into 12, that is 27.7 ampere root meter. What is K1C, by the way? 24. What did I get? 27.17. And hence, will it fail or not?
Yes, sir.
It will
Yeah.
fail.
So hence the crack will fail. So that means this wall cannot withstand that kind of a load. Okay. Now you can define safety factors. Safety factor for fracture can be defined as K1C by K, isn't it? And K1C is FC Sg root pi AC, where FC is evaluated at AC. FC is your geometric correction factor. And this is what you call safety factor in stress intensity. You can also define safety factor in crack length. Right? Safety factor in crack length is AC by A, where AC is the critical crack length divided by the existing crack length. Right? And this is F by FC times XK whole square. So you don't worry about this equation. This we will get later. But AC by A, that is critical crack length. How would you calculate critical crack length? If you are applying certain load, right? For that particular load, what will be the critical crack length you can compute if K1 is less than K1Z. Now the factor of safety in crack length will be AC by the current crack length. Okay. So now let us look at the relationship between G and gamma. We know the crack length A is equal to 2 gamma E by pi sigma square, and G1 we know that 2 times gamma. Right? So now A can be written as G1 E by pi sigma square, or G1 is equal to sigma square pi A by E. What is sigma square pi A? That is K1 square, isn't it? Because K1 is equal to sigma root pi A. If you take square of that, sigma square pi A by E, pi A. So now I can write G1 is equal to K1 square by E, where G1 is the energy release rate, K1 is the stress intensity factor. That is how they are related, G1 and K1. But what is the difference? Both of them allow us to talk about fracture, but G is a global quantity. So what I'm talking about whenever I'm talking about G, I'm talking about energy release rate in the entire specimen. Whereas K is telling me what is the intensity of the stress at the crack tip. That is why K is a local quantity, G is a global quantity, both of which are suitable for assessing whether the failure is going to happen or not, whether the fracture is going to propagate or not. Is that clear? The relation between G and K?
Yeah.
Okay. So now we have talked about K1C, right? So what are the standard methods to measure this fracture toughness? So there are ASTM standards, particularly the ASTM E399-90 is the relevant standard for measuring plane strain fracture toughness. Plane strain meaning the loading conditions are such that the strain in the outer plane direction is 0. So here if you take an ingot, and there are various ways that you can cut a specimen which is having some texture to it. This is direction of rolling. Suppose if you have a specimen which is forged, and then there is a rolling direction which will create a texture. As a result, you will have some grain orientation, right? And hence fracture toughness depends on the direction of the loading and crack orientation. So there are 6 specimen geometries that are possible. One is the longitudinal direction. So this is called LS, right? This is longitudinal, and this is short transverse. Longitudinal short transverse because the crack is in that plane. And this is transverse and this is short transverse. Depending upon how you are cutting the specimen, this could be LS, SL, ST, TS, LT, TL. Okay. These 6 specimens are possible. And usually you can cut the specimen, but there are more details. So you actually cut a specimen like this. This is what we call compact tension specimen, CT specimen, or you can also cut this specimen that is called 3-point bending specimen. TPB means 3-point bending, meaning here you have a support, here you have a support, and you will apply a load here. So that is why 3-point bending. And you cut a crack in a specific manner. So you particularly drill a hole and then you actually use an extremely sharp laser cutter to create a crack of certain length, and then you say that this is my crack length so that the crack tip is sharp. Similarly, you have to do that. And you create this such a geometry so that you can keep a strain gauge in this area, so that when the crack is deforming, these points, when you're applying the load, these points will move apart, right? Then that deformation in that direction or in this direction can be measured locally by putting a strain gauge in this region. Suppose if you add a strain gauge, the strain gauge gets extended, isn't it? When the load is applied in the tensile direction. here and in the bending direction here, this distance increases. Then that is what we call crack opening displacement. So that is something that we can measure by keeping a strain gauge there. And based on the data that we measure, one can compute the K1C, right? So once you have measured data, let us say if the measured data is to be used confidently for a given B, means out of plane thickness B, then your crack length that you are starting should be greater than 2.5 times K1C by sigma y square. Only then you can use the measured K1C. After measuring the K1C, you need to check this condition. If this condition is satisfied, only then the measured K1C is useful, otherwise you cannot use it. Okay. Why? This means we need to have a prior knowledge of K1C. If this is the case, then we need to have the prior knowledge of K1C. That is only then you can cut the A, otherwise you cannot cut what should be my specimen crack. So, and hence there is an alternate guideline. You can find B and A in terms of the ratio of sigma y by E. So there are several guidelines. You will follow those guidelines. I am not going to talk about all those guidelines, but the general way that it needs to be measured is what I am going to describe. And most importantly, you need to machine the specimen to the specified tolerance and surface finish, because if your surface finish is bad, that can measure a wrong fracture toughness of the material. And machined notch should be finished into a chevron notch to prepare crack with a straight front like this. So how do we do that? Usually either you use a very sharp laser gun, which was not there available in the earlier days, and hence what people were doing is they are taking this fellow and then first preloading it so that they create a fatigue crack of known dimension to avoid large scale plastic deformation. Right? They do a fatigue crack between these two values and then create a sharp crack. And always the loading rate is maintained to be 0.55 to 2.75 ampere root meter per second. When you do that, you will measure the load that you are applying, P, versus COD, crack opening displacement. That is the distance that the strain gauge shows here. And when you do the load displacement curve, you can observe three kinds of load displacement curves. And you would say, you would identify this PQs. For example, if you look at type 2 curve, you have clearly two clear maxima, isn't it? If you have two clear maxima, then PQ is very clear. PQ is your fracture load. If P max by PQ less than 1.1, else the test is invalid. You need to redo the test. If P max by PQ is less than 1.1, you can use, otherwise the test is not valid. That means something else has gone wrong and hence you need to redo the test. If you are able to identify PQ very clearly, no problem, like type 2. You also can have type 3, you will not see P max, you will only see PQ. That's also fine. If you don't see P max and PQ exclusively, then the way to identify PQ is to draw a line parallel to 95% of the slope of the elastic line. We know slope of the elastic line, 95%, 0.95 times the slope of that line will be this line, and that will be your alpha. And wherever that line cuts this fellow, that is going to be your PQ. That is the universal guideline. For a CT specimen, if you measure that PQ value, that means wherever the fracture happened, then the fracture toughness KQ measured at that PQ is given by this formula, where f of r is given by this geometry. R is equal to A by W. What is W? Here, this is A and that is your W. A and that is your one, this is your W for a CT specimen. For a 3-point bend specimen, W is different. So you plug in this equation. This is derived by people with several experiments, and then we will take them as an empirical relation and then measure force PQ and then compute fracture toughness. Okay? KQ, you will consider the computed KQ as fracture toughness if B comma A, both of them are greater than 2.5 times KQ by sigma y whole square. Otherwise, you have to start the experiment again with a different A value, because you are starting with some A value, and if that A value does not meet these requirements, then you have to restart the experiment. Okay? If you know the materials K1C, then you can actually compute A to be much smaller than A to be little larger than that, so that there is no plastic deformation whatsoever possible, so as to make this KQ as purely elastic fracture toughness. Okay, is that clear? Any questions here?
Sir, how this 3-point bending test is initiating a mode 1? Actually, the load directions are different.
Load direction is different, but if you are loading like this ahead of the crack tip, it will experience an axial stress, right? Sigma 11. It's a bending problem, no?
Okay.
It's an axial stress that is locally experienced. That axial stress is what is causing this crack to open, isn't it?
Okay. Okay.
Any other questions? Okay, if there are no further questions, we will stop it here. And we have to start the fatigue failure that we will start in the next class. I don't want to start today, but I would like to understand how you guys have done the exam. So were you able to answer all the questions within the given time?
Sir, time is not a problem, sir.
Some of the problems they are not able to solve, sir. Actually.
Why? All of them are more or less close to what you have done in the
Sir, first problem little bit
tricky.
tricky. That is what that itself takes much time, sir. That's what.
That is why you should not solve the first problem. If it is tough, you should move on to problems that you know.
No, sir. That was eye-catchy, no, sir. Some figure you are given. So only we thought that it is a non-primitive. So we draw all these things and put the triangle also in the second sum, and then also. Yeah,
because that is you need to think out of box for that to identify the primitive unit cell.
Yeah, that is we are all are not aware of that, sir. So
I know that now I did not teach, but I have taught you the concept of primitive unit cell, right?
Yes.
So you have to have one
atom
per
unit
unit cell.
Well, that is point. Yeah, per atom. So theoretically we know, but we are not able to imagine how it looks like, sir. That is the only thing we missed out.
So do you know the solution now?
Yeah, we found the solutions.
Yeah, good.
Sir, can we get that question paper? Actually, we were not able to get
Question paper. Question paper, can you get it, sir? Because we
I
are.
will send you. I will share it through Femina and Subbalakshmi, and they will share it with you. Okay.
Also the answer sheet, sir.
Sir,
I will correct the answer scripts in 1 week's time and then share it with you. Okay.
So the answer key we are.
Sir, answer keys. We know that some of the problems we are not.
No, now what I will do is now I will share the question paper with you. Okay. You find the answers and share it with me. You solve.
Okay,
now it's not an exam, right? So you can
Yes,
work
sir.
fully.
Sure, sir.
Yeah.
We will do it, sir.
Rather than me giving you the answers and you not consulting ChatGPT. Don't consult ChatGPT or any AI tool. Try to find on your own. Okay.
Noted, sir.
Yes,
Noted, sir. We will do it, sir. Not a problem.
Okay. Any other question?
Sir, only humble request. We need some lenient correction from your side, sir.
No. The humble requests will be heard, may not be implemented. You are free to put forward your request.
Okay.
Yeah. Anyway, we'll see. Don't worry about it.
Thank you, sir. Thank you, sir.
Thank you so much, sir.
All right. So we'll meet tomorrow. Today I don't want to start the fatigue. We'll start afresh in tomorrow's class. Okay.
Okay.
Maybe
Sir-
tomorrow we may extend by 10-15 minutes if that is not a serious trouble to you. Okay?
Yes, sir. Sir.
Okay, sir.
Okay, sir. Okay.
Sir, one question or 1 point.
Yes.
So, Femina informed us about the polar moment of inertia. I think you told her to inform us, but we got that information almost 5 minutes before the exam.
I expect you to remember polar moment of inertia, right?
Yeah, we have used that, sir. We have used the
Then
formula.
it's fine
But yeah.
because someone asked. So I didn't have means to communicate to all of you. Someone asked. So then I thought, okay, I initially said I will not give, but then I thought, okay, if you are only losing all the marks because of that, I thought, I know, but did you lose marks because of that?
I mean, I have done that, but not sure, so I know the formula, so I have used the formula to derive that J. So yeah, but getting the value earlier would have helped.
No, but polar moment value I have not given. Formula I have given.
Oh, okay.
Okay.
Yeah, then formula we have used, sir. Yeah.
Yeah, formula if you have used, no problem. Okay.
Okay.
Anything else? All right, then see you. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.